We present streaming diffusion policy, fast policy synthesis with variable noise diffusion models. Diffusion models have seen rapid adoption in robotic imitation learning. However, action synthesis is often slow, requiring many steps of iterative denoising. This limits the extent to which these models can be used in tasks that require fast, reactive policies. To address this, we proposed streaming diffusion policy, or SDP. We leverage the insight that generating a partially denoised action trajectory is substantially faster than for a fully denoised action trajectory. At each observation, our approach outputs a partially denoised trajectory with variable levels of noise corruption, where the immediate action to execute is noise-free, with subsequent actions having increasing levels of noise and uncertainty. In this way, SDP operates in a streaming fashion, only fully denoising the actions that are presently needed for execution. Our SDP approach synthesizes a persistent action buffer consisting of future actions to execute. We initialize the buffer to have increasing levels of noise corruption. By running a few steps of denoising of this trajectory, conditioned on the current observations, we have the first action clean and ready to be executed in the environment. After execution, we append a Gaussian noise action to the end of our buffer. This again forms a trajectory we can denoise with newly given observations. SDP is able to learn several manipulation tasks, such as picking up deformable objects, block stacking, and a peg-in-hole assembly task. These are complex, long-horizon tasks that require fine-grained manipulation. Another challenging aspect of these tasks is that the demonstrations include longer sequences of slow, precise movements. This can result in other imitation learning algorithms getting stuck during rollouts by pausing indefinitely. We systematically evaluate SDP against baselines on a real-world push-T setup, where the policy pushes a T-shaped block into a goal area, given proprioceptive sensing and camera observations. Our method achieves a high score, while significantly increasing the prediction speed compared to previous state-of-the-art. We observe that the most common failure mode for diffusion policy and consistency policy is that they get stuck performing small oscillatory movements when attempting precise and slow pushes of the block. This is due to their constant action replanning over action trajectories. In contrast, SDP has a persistent action buffer across observations and is less prone to this error. In addition, we benchmark SDP on the simulated push-T task and several tasks from RoboMimic. We find that it is able to complete complex tasks from image observations and performs on par with state-of-the-art baselines while increasing the prediction speed.